Okay, so we just got finished talking about the terrestrial hydrosphere. I don't know if you took a break and you were like, I need a day to absorb all this amazing information about river systems and the Skagit River and how living on the Skagit River is super dangerous. Or if you jumped right into this video to go from terrestrial to marine hydrosphere. So again, geologists sort of split the hydrosphere up into two entities. The terrestrial hydrosphere, which we just learned was any of this fresh water that is sort of um, dynamic on land. But now we have to jump to the marine hydrosphere, which is all the salt water, which is in the ocean, which I love. We just live in the coolest area where we live so close to the salty Salish Sea, and we have such an incredible dynamic Skagit River. Our hydrosphere here is so beautiful and incredible, and I hope you guys leave this class with a greater appreciation of where we live, and the really cool, amazing place that we live in. So we're going to go back and discuss drainage basins. We're going to talk about ocean composition, ocean salinity, ocean layering, and the conveyor belt. Here's some new vocab for you. We're going to do a little chemistry. Brace yourself. Not anything crazy. We're not going to get crazy, but we are going to talk a little chemistry. So we're going to go back to the drainage basin in this image here, which depicts the terrestrial hydrosphere as part of how it works on the land, how it moves on the land, the freshwater systems available to us on the land. But we started up here and we worked our way through weathering and chemical weathering and groundwater and then eventually to stream systems. And we ended the terrestrial hydrosphere lecture on deltas. And the delta, if you remember, is the mouth of the river where the river system meets the ocean. And the velocity of the river system slows and starts depositing material right at the mouth of the river, creates a delta. Today, we're going to enter the ocean and talk about the ocean. And I know a lot of people are like, well, what does this have to do with geology? Um, I get this question a lot. And so my focus in, well, undergrad and graduate school was in geochemical oceanography. So I studied sort of the geologic relationship with the ocean. And it is so incredible. I mean, all of these spheres that I talk about in this class are all interrelated. You can't really talk about one without talking about the other, which is why I sort of set this class to do a sphere for each module. So I know the ocean is sort of a step back from rocks and from tectonic plates, but it is so integral into Earth's systems and how geology functions that I had to talk about it. I have to talk about the ocean. So we have to start with, and this is so geologic. People don't think about how geologic the ocean composition is. But we're going to start by talking about what the ocean is comprised of. So I actually just got this question the other day from a 10-year-old. Oh, I loved it so much. They zoned out after I got into like the third or fourth sentence, but you can't do that. You're taking a whole class on it. So how did the ocean form? So we believe, scientists believe, and to be completely honest, we're still studying this. We don't have full evidence that this is entirely where the water came from as a whole right now. In fact, we're learning some other interesting relationships between different reactions that are actively happening right now, meaning um, what we believe is that when the Earth formed 4.6 billion years ago, it was a fireball of death. It was molten and liquidy. And 4 billion years ago, so this was 600 million years after Earth's initial formation, the temperatures and this molten lava-y Earth structure began to cool. The Earth's surface began to solidify and the atmosphere formed. And the atmosphere is sort of like a blanket. We're going to learn about atmosphere in the next module. The atmosphere really held things in Earth's systems. And because of this, as the Earth was still forming, because it was still actively forming at this time, 4 billion years ago, it was just less molten. There were volcanoes, there were volcanic eruptions, and volcanoes were outgassing a bunch of different compounds, sulfur dioxide, carbon dioxide, methane, water vapor. And so what scientists are finding now too is that there is a chance, I think there's a picture, yeah. There's a chance that right now, Earth is actually creating water from these chemical reactions, as it were. Uh, So this idea, and maybe you've never heard this theory before, but there's this idea that Earth has only had ever the same amount of water as when it started. Evaporation, and then it turns into rain because of this water cycle. But we're learning that's not true. And in fact, some water escapes out into space if it reaches high enough altitudes. And some water is being, we believe, reformed at Earth's surface. Um, oh, I also don't know why I didn't bring this about. So this was the formation of the ocean, but water also formed or came to Earth through meteorites. That's what we believe. That's where we believed initial water and the immense volume of water that Earth has. As Earth was in its fiery molten form and temperatures cooled, we had a bombardment of meteorites that was significant and significantly higher than what it is today. And these meteorites brought with them ice and water and hydrogen and oxygen that then bonded and formed water. So the water itself came from meteorites and from this volcanic outgassing theory. So now we have this beautiful ocean. But as you can imagine, the ocean, when it first began to form, wasn't entirely salty. We know the salt, the water, oh my gosh, we know the ocean is salty today. Hopefully you've never drank it. Don't do that. Um, but how salty is it? Is it salty equally everywhere? And why is it salty? Where does the salt come from? Also, speaking as a scientist, we should probably stop using the word salty to describe the saltiness of the ocean. Listen, if you say it to my face, I'm not gonna be mad. If you're like, wow, the ocean is salty, I'm not gonna be like, actually, it's salinity. Like some pompous old white geologists that I know. I'm not gonna be that person. But the proper and technical word to define the saltiness of the ocean is salinity. How saline is the ocean? And this salinity describes the ions or the chemicals that are present in the water. We've talked ions before. I brought them up in the last module and this past terrestrial hydrosphere. But if you've never taken a chemistry class in your life and you don't know what the word ion is, it is basically a compound that is slightly charged. I'm going to jump ahead just briefly. So these are chlorine and sodium ions, and they hold a little baby charge to them. They're either positive or negative. That's all they are. Um, you don't necessarily need to know how charged they are, why they're charged. What you need to understand is where do these ions come from? So this is the recipe for ocean water. Here is our water. So if we had 1,000 grams of water, 965 grams of those would be straight pure water. And only about 35% of those, sorry, 35 grams of those is going to be salt, different salts. And salts are these ions, these charged particles over here. Now, the salts that make up the most part of this salinity is sodium, boop, 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 and chlorine. Sodium has a weird element symbol, it's Na, and then chlorine is Cl. We also have sulfate, magnesium, calcium, potassium. We have strontium, bromine, carbon. So where do these ions come from? Remember when we talked about weathering, chemical weathering, and the great candy mountain, as it were? And as the water rains down on this candy mountain, then the sugar dissolves at the top of these mountains and is sent down these river systems. And remember, I said that Candy Mountain was a metaphor. And it's one of the best ways to sort of visualize how uh, rocks eventually dissolve over the time and that sugar will make its way down the river. Well, the sugar is not sugar, right? And I said that a few times. It's just a metaphor. The sugar that I'm depicting are these ions. And I mentioned calcite was a big one, silicate was a big one, but sodium is part of an old mountain system. Chlorine is an old mountain system. These particles have been dissolved as part of this chemical weathering process. They've been brought down these stream systems and they have exited and deposited out into the ocean. This is what makes our ocean salty, is the weathering process from these mountains. So it's a very geologic process that then makes its way down into the ocean. And as you can imagine, these salts don't really go anywhere. They might settle at the bottom of the ocean eventually. There is a whole system of like organisms need a lot of these salts to survive, um, and they will consume them, but they're not evaporating in the same way that the ocean is evaporating. So theoretically, the ocean is just going to get saltier and saltier, which isn't a bad thing. Don't think of that as being a bad thing, but it is going to get saltier and saltier because more and more weathering is going to take place. And it is part of a cycle, so it's going to mostly be in equilibrium. So it's not something we have to panic about. That's not the same as saying, like, the ocean is acidifying. That is a completely different concept. But it is important to note that these salts aren't necessarily being evaporated in the same way that the ocean water is. Um, Oh, this is just me describing the per mil, which is this per thousand, which I discussed. If you have 965 grams of water, 35 grams of those are these salts. And most of these salts are sodium and chlorine. And sodium and chlorine, when they bond together, they form sodium chloride. This is the mineral halite. So there's an actual mineral that has sodium chloride. But if you're not familiar with sodium chloride, all that is table salt. That is table salt. So it's a very common substance, harmless substance. And in the water, if you've ever tried to dissolve, Henriette's licking me right now. Okay, well now you stopped. I don't know what you want. It's not lunchtime. If you've ever dissolved salt water and it leaves behind these beautiful salt crystals, um, or I'm sorry, if you've ever evaporated salt water and it leaves behind these salt crystals, and then you've poured more water into this dissolved substance, the salt dissolves. So the salt isn't just chunks of salt hanging out in the water, right? And that's because when you put water with sodium and chloride, they actually dissociate. So they sort of spread apart and they bond with the water molecules. And that's actually a very important part of this salt system is that in the ocean, these salts are dissolved, and that allows a lot of these marine organisms to consume these salt products and nutrients, basically. You've seen this slide a few times now because I keep coming back to it, but these are just the inputs and outputs of different salts. So I did mention that there is a bit of a cycle with that, and sometimes the salts get embedded in sediment and they get buried in the ocean. So it is basically at equilibrium. Again, it's not anything we need to panic about. So ocean salinity is a very important proponent of the ocean, but is it equal across the ocean? You would think, well, yeah, it's one major solution. It's a giant solution of water. Why wouldn't it be equal? But it's not. Seawater is not equally saline everywhere in the ocean. The Atlantic Ocean has different salinity concentrations based on its geographic location and the processes that are occurring in those locations. So, what could explain the salinity being so different? And it's giving very specific latitudes. And again, latitudes are important to know, but think about why is ocean salinity so different from like the north part of the Atlantic Ocean to the central part of the Atlantic Ocean? Why is surface salinity so low near the equator of the world? To be honest, this is suggesting the Atlantic Ocean, and it does change in the Atlantic, but it's especially low near the equator. Hmm. And higher uh, in other regions. So the equator has relatively, hi, baby, relatively low salinity. Here's the equator. This low salinity is about here. This is annual average surface salinity. So our blue colors is 33.5, is lower salinity. And I believe this is parts per million. It doesn't actually say. Ugh, that's rude. So every thousand. I know said, okay, I'm so sorry. I know I say parts per mil. Um, it is one of the most annoying parts of science. I had to learn this in my thesis. Let me go back to this slide. This symbol here, okay, I am so sorry that this is going to get really confusing, is technically parts per thousand. but we denote it by per mil, which is also short for per million. Listen, I did not write science. This is not my fault. This symbol, instead of percent, is per mil, but it takes into account um, parts per thousand. So when you hear me say per mil and you're like, per million, but she's been talking about per thousand. I know. I'm really sorry. This is per mil, but it's denoting that for every 1,000 grams of water, we have 35 grams of salt. So that's all that means. And I'm really, really sorry. Okay, let's go back to this. So per mil, for every thousand, so basically what this is saying, for every 1,000 grams of water, the blue color is 33.5 grams of salt. For every 1,000 grams of water, 36.5 grams of salt is the red color. So the Atlantic Ocean is crazy because it's incredibly saline, but most of the salinity is sort of through these gyres here, which we'll learn here in a second. And we have lower salinity up here, and it kind of lowers through the equator. And we definitely have low salinity in our Antarctic region and up in the Antarctic. I'm so sorry, up in the Arctic area, Arctic area. So why is it so different? And you'll note, I mean, 36.5 and 33.5, they're not majorly different, right? Like it's 3 parts per million different. That's not a lot. So it looks very dramatic on this map. But in whole, it's not a huge difference, but it's still different enough that we have defined this scientifically to say there's more saline in some of these regions than there are in like the equatorial regions or in the North Pole and South Pole area. Why would we think that is? There are a couple factors that lead to this. Um, Evaporation of seawater. How do you think that that will change the saltiness, right? So if we're evaporating this water, the only thing that's coming out of an evaporation process is water, meaning that if we have high evaporation occurring in regions like this and in regions like this, there's a lot of evaporation occurring because it's warmer. That's going to leave behind more salt. More evaporation equals more salinity. How would stream flow into the ocean change the salinity of seawater? Let's find a good one here. Um, Here is India. This is the Bay of Bengal. This is where major river systems are exiting into the ocean. Look at how fresh this is. That's because we have an abundance of fresh water, making us high. Henry is tapping inappropriate parts of my body right now. Stop, baby, stop. We have a huge amount of fresh water inundating into the ocean. This is causing these oceans to become less saline. So more fresh water inundation is going to equal less saline. What about, this is one of my favorites, the freezing of seawater to form sea ice? If we have, so let me go back again. Here is Greenland. Greenland is doing a couple things right now, and I guess Antarctica and the Arctic are also doing a few things as well. Uh, Greenland is absorbing, actually, you know what? This is going to be a better depiction. This area here and this area here are two areas in which we have seawater that are actively being frozen because these little inlets here generally tend to have more sea ice or ice that sits over the ocean as a whole. So these are good areas to sort of depict. Greenland gets a little crazy, so I think this will be easier to explain. So these areas down here in the end, oh my God, Henry, she's being so dramatic. These areas are forming sea ice in wintertime. So on average, on annual average, there's a lot of ocean water being pulled up into um, into ice. But salt doesn't freeze. Salt won't freeze. Salt will stay behind. The only thing that's going to freeze is this water. So you'll know in this area here we have a lot of blue, meaning we have less salinity around Antarctica. But there's these weird little high saline areas in Antarctica where sea ice is actively being formed pretty much every winter, meaning that it leaves behind higher salinity. So when we have freezing freshwater or freezing ice from the sea. This is kind of a confusing way to say it. When we have freezing seawater, it leaves behind the salt, making that ocean more saline in that area. And then finally, how does a glacier moving off the land and into the ocean and melting change the salinity of seawater? Well, let's go backwards, right? So we are, um, let's go back to this one and the Arctic up here. So we have a lot of, this is kind of sad. We'll learn this in the cryosphere too, in the cryosphere module. But up here in the Arctic, we have a giant ice sheet. And this giant ice sheet just sits over the ocean. It doesn't sit over land in the same way that the Antarctic and the Greenland ice sheets sit over land. This ice sheet sits just over water. This is sea ice, and it is actively melting pretty severely. So you'll know some of the lowest salinity that we have is right here, 29, 30, versus our 36, our 35, our 37. Henrietta. Um, we have a bunch of fresh water, because remember, ice doesn't have any salt in it, a bunch of fresh water that is just melting consistently in this area, meaning, oopsie, that melting fresh water is going to make that less saline. So depending on the processes that are happening on this map, it's going to contribute different salinity levels to different areas of the ocean. Most of the precipitation that we see in the world tends to happen around the equator. So this is annual precipitation, and it doesn't give us units, which is really annoying. I'm going to assume it's centimeters. That's usually, it could be centimeters or inches, so forgive me. I don't know, it doesn't have units. 90 inches. If it's annual, it's got to be inches, because we do get about that much in this area, about 90 to 100 inches of rain a year. Meaning that most of the rain, so 300 to 330 inches of rain, hit the equator every year. This is where we see high precipitation. And because of that, most of the equator has lower salinity than its mirrored counterparts here. So we have this gyre that has high salinity, this gyre that has high salinity, but then we get this little bloop here. So what this is telling me is that this is generally where we're getting most rain. So it's not right on the equator. It's a little bit north of the equator. Here, this little dot here is Hawaii. So this whole area here just gets an abundance of rain. Oh yeah, see, here's the equator, and just right above it gets an abundance of rain, and we see that every year. So precipitation has a lot to do with uh, your ocean salinity and the difference of salinity. This is a map that depicts evaporation and precipitation. And I don't think this one is as important, but basically what we're depicting is where we see more precipitation. We generally tend to see a little bit more evaporation too, because that's where the warmer temperatures are. And evaporation will eventually turn into clouds, which will turn into precipitation. So let's talk about, this was all on surface, mind you. So all of these maps that I just showed you were surface level salinity and surface level currents. But obviously the ocean is deep, and different things are happening in deep parts of the ocean versus surface parts of the ocean. So this is the Atlantic Ocean. Hi, sweet baby. This is a cross section, probably of the Atlantic Ocean, but I think it might just be a general cross section to depict if we have, so these are our lines of latitude. This is saying this is our equator. This is 60 degrees north and 60 degrees south. This is a north-south cross section of a generic ocean. Sorry, I thought it was Atlantic. I lied to you. Of a generic ocean. These three zones are defined by different densities. The deep zone contains, which is 80% of the depth scale here. So 80% of this cross section is the deep zone. And it is incredibly dense water, which is why it's sitting on the bottom. The reason that it's denser is because salt water sinks. Fresh water will stay on the top. So, in the 2021 floods, November floods, I was in Bellingham at the time, so I got a lot of information about the Nooksack. And the Nooksack emptied so much fresh water into Bellingham Bay in that 5 day period of flooding that you could dip your finger into Bellingham Bay, which is a saltwater entity. You could dip your finger into it and it would be fresh water because the fresh water was just inundating the surface of the ocean water. And because it's less dense than salt water, it was remaining on top. Now it will all mix eventually, but in that immediate time of the floods and for a little bit afterwards, you could dip your finger into Bellingham Bay and you couldn't taste salt. Still don't recommend doing that. There's a lot of fecal matter that goes in Bellingham Bay, but my colleagues were telling me like it was incredibly fresh, and the depth of fresh water was very high during those flooding events. So, an increase in salinity is going to increase the density of the water, and an increase in temperature is going to decrease the density. Our deep ocean is both very salty and very cold. And I also want to bring us back to when I was talking about plate tectonics and we looked at convection. Heat rises, right? As a convective cell, that heat is going to rise. Obviously, ocean water isn't hot, but there are parts of the ocean that are warmer, and all of those warmer currents are going to slip to the surface while the colder currents go to the bottom. So we have cold, salty water that sits at the bottom of the ocean, and we have warmer and still salty, but less salty water that sits on the surface. So these are major surface ocean currents. So these are surface oceans. We're going to talk about the conveyor belt here in a second. Hi, baby. I love you so, so much. Um, Stop it. Oh my God. Don't have children. I love them so much. I love them. And obviously they're cats, they're not children, but they are being so needy. And I love them so much. So we have cold currents are the blue. Warmer currents, so the Gulf Stream, this is an important one. The Gulf Stream is a warm current. Do you play with this one? You're gonna play with Google Maps, or sorry, Google Earth Pro for this lab, and I think you do look at the Gulf Stream. The Gulf Stream is incredibly warm. Um, okay, the other anecdote that I'll say, sorry, I keep going off on bird walks, is if you've ever watched the movie The Day After Tomorrow, which highly recommend, the premise is they're in New York City and they're talking about climate change and oh God, I don't remember the actor's name, but the lead actor who plays the scientist, who's the dad, he's basically like, the Gulf Stream currents are changing. These currents are starting to change. And because of that, it's going to change climate. Now, listen, if you talk to any scientist, the premise of it and the context behind it, absolutely true. If we start to change these currents, it will change the climate and it could change it dramatically. But the rate at which everything changed in that movie was so absurd. I love these movies so much. It's one of my favorite movies because it's so bad. But the idea behind it was accurate. Some writer got a hold of the idea that if we change these ocean currents, it will change the climate. And he was right, but he was like, let's do it so fast. This will take like hundreds of years to actually change. And we're not going to see some crazy ice cyclone work its way across the land. Highly recommend the movie. Um, Part of these currents form what we call eddies. So I also got this question from a friend a little while ago. Basically like, well, how is the ocean perfectly flat? Because when you put water in a glass, right, you see a level at which it sits. And no, it's not. We get these crazy eddies. We call them eddies. I'm so sorry. We call them gyres. Eddies are the spinning motion of the water. The gyres are like bulges in the ocean. Yeah, here's an eddy spinning. Uh, but these gyres are like bulges in the ocean that happen because of the circulation of the ocean. And they happen because of different currents moving in different directions. So water moves to form surface currents, which will form these bulges in the ocean. They're defined by their relative temperature, warm or cold. We're not getting crazy. If you really, really want to dive into oceanography, yeah, we talk more about like, oh, this is 35 degrees Celsius versus 36. But these currents are either warm currents or they're cold currents, depending on where they're coming from geographically or if they're coming from lower surface or higher surface in the ocean. This is an infrared image that shows that really warm Gulf Stream mapping out towards the north. And these green and blue colors are colder, respectively. So there's this cool place in the ocean where you can see this line of demarcation, basically, and you see two different ocean densities and temperatures coming in contact with each other. And they don't mix easily because they're in entirely different temperatures and they're entirely different densities of water. So gyres are circular currents unique to the hemispheres and these bulges. How do they form? What is different about a gyre in northern and southern hemisphere? Uh, Western. Hold on a minute. Come in. Okay, so what I love about online classes is that as I'm going through slides and I get into this rhythm of what I'm talking about, I might miss something like initially, and then when I realize I've missed it, I can pause the video and find it. It's just less awkward than doing it in person when you're like, wait, I gotta look this up. But I do talk about this process in the next module and at least in more depth. So I'm not going to dive that hard into the definition. But what I do want you to understand is that the Earth is rotating, right? Hopefully, we're all aware of this. This is middle school science. The Earth is rotating, rotates every 24 hours. Um, this is how we get our days and our nights. It's really important, right? The Earth is rotating, but the Earth rotates at a different rate along the equator than it does on the poles, meaning that the poles to get from, okay, I'm trying to explain this without sounding too confusing. Um, the poles are sort of moving a little bit faster. It's a bad way to describe it too. Um, okay, hold on. I want to describe this well. Okay, I'm glad I looked this up because first of all, it was backwards, so this was great. And I think this helps describe it too. So this is from NOAA. We love NOAA, the National Oceanographic and Atmospheric Administration. Um, and they have some really great websites that depict a lot of these scientific concepts very, very simply. So to put simply, the spinning of the Earth is also called the Coriolis effect. And the way that the Earth spins is different based on the latitude of the Earth. And I said that the poles spun faster, and I was wrong. The equator moves just a little bit faster, because it has to get from one point to the same point at a much larger distance, a much larger circumference than, say, a spot on the pole. The pole circumference up here is much smaller, right? So we have to go from the equator, which is a circumference like this, to a pole, which is like a circumference like this. And basically, because the Earth is spinning at an equal rate, the Earth is spinning at an equal rate. The location of the poles from here to when it gets back to here takes less time than if I go from here and then I wait for the same spot in Africa to come back. It takes more time. So the idea is that the Earth is moving at different speeds because of how much surface area um, the Earth has to cover to get from point A back to point A as the Earth rotates. And if this is really confusing to you, that's okay. I'm not about to test you on define the Coriolis effect from the North Pole to the South Pole. All you have to know is that the Earth sort of moves at different rates based on latitude, and this affects the ocean. So this is what I was getting. And I added this slide. Oopsie. Go back to normal. From current slide. So because of the spinning of the Earth, the ocean currents actually move in different directions in the northern hemisphere than they do in the southern hemisphere. And there is another story basically of like if you flush a toilet in the northern hemisphere, it goes one direction. And if you flush it in Australia, it goes in the other direction. And this is true. And that has to do with the way the Earth is spinning and the Coriolis effect basically altering the direction in which these currents are going and the way that they want to sort of spin into these gyres. So when I was talking about gyre and then I asked, what is the difference of a gyre in northern and southern hemisphere? I meant to talk about the Coriolis effect and I didn't. We're going to dive more into this in the next module, atmospheric module, because it's definitely more integral in atmospheric sciences. We also get circulation. So we get these ocean currents surface that sort of spin around the Earth. But we also get them come up from the bottom of the ocean and then sink down to the bottom of the ocean. When the cold, dense water rises from the bottom of the ocean, we call this upwelling. And it's a really, really, really important proponent of ocean currents and the ocean system because this upwelling also brings nutrients, whether that is plankton, whether that is those ions that I was talking about that a lot of organisms need. So this upwelling is incredibly important for fish and for, hi, sweet baby, and for other marine organisms to survive. However, there are areas in the world, and this is happening in Greenland. So this is also why I mentioned that Greenland was a little crazy, in that Greenland has these warm waters coming to its southern base in the Atlantic Ocean. Let's just go to that map. Nope, not that one. This bad boy. So Greenland up here. Greenland has warmer surface. This is salinity. This is a map for salinity, not temperatures. But basically, the idea is the Atlantic Ocean has warmer waters hit um, oh my gosh, Greenland. And that warmer water gets very dense. Starts to mix with colder water from the Greenland ice sheet. So the Greenland ice sheet is actively melting into the Atlantic Ocean. And it's forming colder water. That colder water is becoming denser and it will sink and mix with more salt and start to flow southward. So we have dense, cold, saline water that will sink, and eventually it will make its way back up in different regions of the world. We get some upwelling on Washington coast in the summer. It's really, really important because that summer upwelling on Washington's coast brings about nutrients. And then eventually it will make its way across the ocean and sink again. And this is part of a system known as the conveyor belt. Maybe you have heard this term before. A lot of scientists actually hate this term. But I think for a 100 level class, it's sort of all encapsulating and it's very descriptive. So the conveyor belt is how the ocean circulates as a single entity, as a whole entity, and it takes into account surface currents, depth currents, upwelling, downwelling, which is just the sinking of this cold water, and how it moves around the ocean as a whole entity, and it looks like this. So here's Greenland. This is where we see the water become cold and dense in the southern part of Greenland. Um, and there are a lot of scientists who would say this is the start of the conveyor belt. So here's where we have cold, dense subsurface, so below surface, cold, dense water flowing through the ocean. And then it goes through the Pacific Ocean. Technically, we have currents that come into the Puget Sound and Salish Sea here that are cold. So we get cold water that comes into the Salish Sea, and then it actually flows back out as warm water. And then we get this warm surface flow that comes down over Australia and up through eastern United States. So this is part of the current that I was talking about that is warm, and then it gets to Greenland again, and then it sinks again. So this is the general overall current of the entire ocean. The formation of deep water is as part of the conveyor belt. This is where super dense waters are formed in a few locations, and this water fills nearly the entire deep ocean. Most deep water is cold and dense. In fact, all deep water is cold and dense. It has to rise to become warm. Um, Open ocean convection, this is when cold winds cool the surface waters until density is greater and they'll sink. So winds will cool it, the melting of ice will cool it. And this happens in the Greenland Norwegian Sea and the Labrador Sea. So if I go, oh my gosh. So this happens here. Um, and it happens. It's here. There's another spot, the Labrador Ocean, where it happens. I want to say, this feels like the only place here that it does it. And the Labrador Ocean. It might be a smaller current than I'm assessing here, but the Greenland Norwegian Sea is basically where most of the warmer, dense water is going to sink. So this is the North Atlantic deep water, and this is me coming back to the fact that warm, salty water is carried to the North Atlantic, but near Greenland, this water cools as this ice sheet is melting, and sinks during the winter. And this water will spill over seafloor sills between Iceland and Greenland, into the main North Atlantic, and we get this beautiful deep water, it's Norwegian Sea, formation that starts here in the Atlantic Ocean. And I think that's it. Oh, JK. Oh, this also happens in Antarctica, as you can imagine, right? As the Antarctic ice sheet is also melting, it's going to form much colder water. And that is predominantly why, oops, we have cool water down here on the Antarctic current. So that is my marine, um, Henrietta wants to say, I'm needy and I love my mom. Yes. That's my marine hydrosphere spiel. I don't think it's quite as long as terrestrial. We're gonna see you next time for atmosphere.